Okay, so we're going to do actually is we're very close to the end of this chapter we've been working on, or this little subject. What we're going to do is we're going to finish lecturing on it right now. It will also help you with what's on tap for today, which is study assignment G, which is about stoichiometry and stuff like that. So since it talks a little bit about solution stoichiometry and study assignment G, and that's sort of right where we left off, along with titrations and stuff like that. I'm just going to kind of finish lecturing on this, and then afterwards, obviously, we'll talk about what will be due. We'll also talk about sort of the exam and all that, and when it will be, and all that kind of stuff. So that's the game plan. We're just going to kind of finish up what we've been talking about here, and then we'll kind of go from there at that point. Okay, so obviously we've been talking about solutions now. Before we talked about stoichiometry, we just finished talking about dilutions. Again, that M1 V1 equals M2 V2 is really what's known as the dilution equation, and it is very helpful in a lot of sort of senses. But typically speaking, when we look at that sort of formula, a couple of things, as I mentioned before. Typically, this side is the more concentrated side. And usually when we solve for V1, it's much like what I drew in that picture a second ago. How much of that more concentrated guy are we going to take out? Again, our twos are usually our more dilute side. And when we solve for something like V2, that's our final volume, our new concentration. And pretty much whenever you kind of make a solution, or even when you are mixing two different reagents, like you grab a bottle of, say, hydrochloric acid, you grab a bottle of sodium hydroxide, and you kind of dump them together. Sometimes people don't realize, that they're actually doing like a dilution when they do that. They're actually diluting it. And again, based on what we talked about earlier, that most solutions that we use, which are reagents, they're essentially water-based. So every time you even take two different reagents and sort of mix them together, even though you're not visualizing perhaps that you're doing a dilution, you are doing a dilution, and you're actually changing the molarity. So if I took, for example, say a 5 molar solution of whatever it is, KSCN, and I took 2 milliliters of it, and then I also took 0.25 molar iron 3, whatever it may be, and I took 4 milliliters of that, and I also added some water to it, right? And just like you were going to make a solution for an experiment or something like that, and say I added 4 milliliters of water. If I wanted to know the concentration of, say, the KSCN in that test tube, when I would put all of those things in, I would put 2 milliliters of my first guy in there of the KSCN. At this point, when I would dump the 2 milliliters in, it's still 5 molar, the concentration. But then I dump my 4 milliliters of my iron in there. This concentration has now changed. Then I dump my 4 milliliters of water in there. Concentration has changed again. So if I want to know what is the concentration, which is sometimes used brackets like this. So when you see this around something in terms of solutions, this usually means concentration, and it usually means molarity. So if I want to know the concentration of my KSCN in this mixture, I could actually use my dilution equation, M1 V1 equals M2 V2. M1 would be the original concentration of my KSCN, which would be 5 molar. V1 would be how much of it I used. M2 is what the new concentration would be. And what about V2? Well, in that test tube went all 3 of these guys, which means my total volume in that test tube is 4 plus 4 plus 2, which is 10 milliliters. And that actually would be my final volume here. And in my made up example here, 5 times 2 divided by 10 tells me that in that test tube, the concentration of my KSCN is actually only 1 molar. It started out at 5, but because I piled on all these different reagents, not necessarily just dump water in there, right? I added some other reagents, which are water-based. I actually just did a dilution, and you can see the concentration of my KSCN actually went down when I mix it in, again, with all those reagents. So sometimes people don't visualize that they're actually doing a dilution in the simple process of actually just making like a reagent that you want to use for an experiment. You're dumping all these solutions together. They're all water-based. You're actually doing a dilution. You could do that for the iron as well. If I wanted to know what my iron would be in this made-up example, my original concentration of my iron was 0.25 molar. The volume that I used to make this test tube was 4 milliliters. And I'll do these guys instead of equals. On the other side, I want to know what my new concentration would be. Again, my iron is in the same test tube that has the same total volume of 10 milliliters. So again, if I take 0.25 times 4 divided by 10, my concentration of my iron in that test tube is no longer 0.25 molar. It has now gone down, as we can see here, to 0.1 molar, because again, we did a dilution on it, even though we didn't go to the sink and add water in a traditional dilution type situation. But this is really a practical application of dilution. This is actually what you are doing when you, again, make a solution from several other reagents, put them all together into one say test tube. And that's because, as we talked about, molarity is again moles of solute per liter of solution. So in this case, every time we add something to our test tube, we're increasing this, and the molarity continues to change. The moles don't change, but the molarity actually does change. Any questions on that sort of aspect of a dilution? That sometimes people don't realize they're actually doing a dilution. Okay. So now that we talked about dilutions, we talked about molarity, we're now going to kind of put together some of those things. We're going to put together molarity, we're going to put together volume, and we're going to put together stoichiometry. And we can do a really solution stoichiometry problem, just like we kind of do a regular stoichiometry problem. The main difference is really how we get to moles. So as we talked about a little bit earlier, typically speaking, when we're dealing with solutions, we're not really going to the balance and getting grams and stuff like that, like we would weigh out grams to moles or something like that. We are typically using volumes and molarities to get to moles. So there's two types of sort of stoichiometry problems that can happen in sort of an experiment. One type of experiment is what is referred to as gravimetrical analysis. And this is a common experiment where you might mix two solutions, as you can see here, solution 1 and solution 2. When we mix it, we can see a precipitate form. So maybe this is silver nitrate, which is a solution, mixed with something like sodium chloride, which is a solution. And as we talked about, this is a double displacement reaction that would produce silver chloride and some sodium nitrate. Now, in this particular case, we may know, because these guys are solutions, we may know the volume and the molarity of each of these guys. And what could we get from the volume and the molarity? Well, if we take liters times molarity, that is going to give us moles. So we could do a stoichiometry problem to figure out how much silver chloride we would make by basically doing the stoichiometry problem using liters and molarity to get to moles. The rest of the calculation would be the same. You would do like your mole to mole relationship. You get your moles or whatever you're interested in, like silver chloride, for example. And then you could use the molar mass of silver chloride to figure out how many grams of silver chloride you would actually weigh out in terms of your product. This could be a limiting reagent problem, like this would be a limiting reagent problem, what I just did here. We have enough information for both of them to figure out the moles, so it could be a limiting reagent problem. It could just be you have only information about the silver nitrate and nothing about the silver chloride, which would make it a regular stoichiometry problem, which again, you would take sort of this route here. If it was a limiting reagent problem, you would do like we did before, again, ice table, figure out the limiting reagent, however you want to do it. The main difference, though, when we kind of deal with solutions in stoichiometry is instead of at the beginning going from grams to moles using the molar mass, again, here we use liters and molarity to get to moles. So that's the major difference between them. So this is one common place where we could kind of use solution stoichiometry, again, by figuring out the moles, figuring out our theoretical yield of something like silver chloride in this case. Now, if you look in this sort of process here, they're mixing the solutions together. We get this solid form. We get a lot of solid form. You can see all that white solid in there. And what he's doing is actually filtering. He's actually doing vacuum filtration. This is actually hooked up to a vacuum line here, and it's actually sucking out basically all the water. So as he pours this kind of solution that has solid in it, all the liquid part, if you will, in this example, it would be the sodium nitrate basically coming through down here. And all the solid white silver chloride, if this was silver chloride, there's a piece of filter paper here. I'll just now make it red. And all the white solid there of the silver chloride is basically sitting on the piece of filter paper at that point. And this is where we talked about where you can introduce some error into percent yield, right? So as you can see, there's a lot of liquid going on. And typically what you would do at that point is pull out the filter paper when you're done filtering. On it should be your solid. And you usually need to let it dry. You could either put it into an oven, let it dry naturally. But this is a case where you could be a little impatient and reweigh it, as we were talking about earlier, where you would still have a lot of that water weight on there. And when you would do that, this is how you would get your actual yield, right? This would be from the calculation, your theoretical yield, and then you could do your percent yield in this case, right? Which is your actual divided by your theoretical times 100%. So, you know, this is a case where error could happen. It's a very common place where error could happen. The other common place is to get a really low percent yield because people rip their filter paper as they're doing this. And you can see this is kind of clear on the bottom of the solution. But, you know, if the filter paper is ripped, you pour too much too fast, you could actually get some solid ending up down here. And the usual will look obviously a lot whiter. Again, I'll use red to illustrate that. And, you know, if you don't realize that you're actually letting the solid go through, again, maybe your piece of filter paper is broken or something like that, that actually would bring your yield down, your percent yield, right? Because you lost a lot of the solid in the part where you get rid of it, right? So that's a couple places where error can kind of happen in gravimetric analysis. But again, we could do sort of a stoichiometry problem just like we did before. Really, the main difference here again is how we go from grams to moles. We don't really use grams moles, we use liters and molarity. Any questions on that there? The other really common way, and the way we're going to do a big experiment coming up here, is with what is referred to as titrations. And titrations is a very common kind of solution stoichiometry problem where in a titration, we typically have one solution that is of known concentration. So we know exactly sort of what the molarity of the solution is. And then we sort of add that solution to another solution that is of sort of unknown concentration. We're trying to figure out what is the concentration of this sort of unknown solution. And we do the titration using a couple of pieces of equipment. This is what a Buret is right here. It's basically a long glass cylinder. And in a lot of cases, we put in either an acid or a base in here. So for example, we could put a base up here. And then we have a flask like in the picture, or a beaker or something like that. And maybe we have an acid down here. You could also reverse it, put the acid up on top and the base on the bottom. Again, you could do either one. And basically what we do is, so for example, this may be your unknown concentration guy. This is something that you know. And what I mean by know is perhaps this is something, say, like sodium hydroxide, where you know the molarity is 1 molar. And down here, you don't know the molarity, but you do know the volume you use. Like, hey, I use 25 milliliters of this guy or something. And you would do this titration by slowly adding, for example, the base in this case to the acid. And you would continue to add in an acid-base titration until you hit something which is referred to as the equivalence point. And the equivalence point in a titration is the point where the moles of the acid equals the moles of the base. So when we do a titration of an acid and base titration, when we hit that point where we have added the exact same number of moles of the acid to the base, that's essentially what's known as the equivalence point, and essentially what is known as the pretty much end of the reaction, if you will. We basically used them up. Both of the acid and the moles basically are going to use each other completely up at that point. Now, when we do the equivalence point, or try to stop at the equivalence point, we sometimes maybe don't stop exactly at the equivalence point. We sometimes stop at what is sometimes referred to as the end point. The end point, much like the name implies, is actually the point where you decide, I'm done with my titration. If you did a good titration, these two guys should be very close to each other. Should be very, very close to each other. But how do I know if I'm adding like my base to my acid that, hey, I should stop? What we use to help us determine where we should stop is what is known as an indicator. And an indicator is really a substance that will change color near the equivalence point. So you will have like a visual representation of, hey, you should stop because the thing just changed color. You're at the equivalence point. You should stop your titration. A very common indicator is used, which is the one that's used in this picture, is one that's known as phenolphthalein. Phenolphthalein is an indicator that's used in a lot of titrations. It is actually colorless in acidic solutions. It's actually colorless in neutral solutions. And it turns a lovely shade of pink in basic solutions. And this is very helpful indicators for acid-base titrations because obviously we don't get into pH and pH scale and stuff like that, but acid and bases obviously are on the pH scale. And how indicators work is they actually work over a pH range. So for example, phenolphthalein here, then this example works over from a pH of 8.3 to a pH of 10. These are both basic pHs. Basic pH is above 7. pH scale goes from 0 to 7 to 14. Above 7 to 14 is basic. Below 7 to 0 is acidic. And 7 right there is neutral. I'll go this way with it. Neutral. So with phenolphthalein, actually, it's colorless at 8.3. Then as you gradually go this way, and I can't really illustrate it well with my pen here, but you get like a tinge of pink that sort of happens. A very small tinge of pink. So light pink that you got to put like a piece of paper underneath it to kind of see the pink. And as you gradually go closer to 10, you get really dark, and we'll assume this is pink, not red, but assume this is pink. You get really, really dark, dark, dark pink. So you get this nice kind of like barely pink over here to this really dark pink as you head towards a pH of 10. And usually when we do a titration where you use something like phenolphthalein, if we kind of just show what is sometimes referred to as a titration curve, looks something like this. This is pH. This is, say, volume of base that you're adding. This is an equivalence point right there. And what happens is in an equivalence point where you would use something like phenolphthalein, it actually is at a basic pH around here, kind of in the 8-ish range, if you will, 8.5, something like that. And basically they tell you when you do a titration with phenolphthalein, you want to stop when you see the very, very first tinge of pink that actually will stay and not go away. Like, again, that very, very light shade of pink that you got to put something kind of white underneath it, like a white sheet of paper, white paper towel, something like that, to actually see the pink in the color in the solution. And when you do that, that means that you're probably right near the equivalence point and you should change. Now, if you wait until your color of your indicator in solution turns this like super dark pink, you might actually be way over here and way far away from your equivalence point. But if you kind of hit it right around where it is, just turns pink, you're going to be very, very close to the equivalence point in terms of volume, and you'll be okay in terms of your titration. A very common thing that is heard when people actually physically do titrations is, you know, they're adding their indicator and they're adding their base in a titration like this. And what will happen is as you're dropping sort of these the base into your flask here, you'll see kind of the pink come, and then the pink will go away. Pink will come, pink will go away. Pink will kind of come and go away. It will stay a little longer, go away, stay a little longer. And you'll gradually see as you do a titration very carefully that as you continuously add, say, sodium hydroxide, that pink color will kind of hang around longer and longer and longer until finally it will kind of stay. And the goal is to get it to stay at a very light pink. This is not a bad example over here. Some people even try to get lighter than that color pink that we see on the right there. Now, it's a very common thing that people will say when they do titrations is, hey, it was like colorless, and I just added 1 drop. And it went from like no color to super dark color. What happens and why that happens is, in my really bad drawing here, let me straighten out my curve here a little bit. There we go. When you reach the equivalence point or approach the equivalence point in a titration, you can see that the pH actually goes pretty vertical. I'm sorry, the pH goes pretty vertical as we get to the equivalence point. And what that means is, in terms of the volume does not change a lot. As you go to the equivalence point, but the pH, which is on the Y, changes a lot, right? It's a big change in pH. So it's a very common thing that happens is you're being very careful, you're adding very slow, and you decide to add 1 more drop. And again, you go from colorless to really, really dark pink. So you kind of jump from that 1 drop all the way back to the end where you got a really dark color pink. And is that a bad situation? It's actually not, because if you're up here, say a pH of 10 up at this range, or you're at the equivalence point, which is like right there, if you just go straight down, it's essentially the same volume, right? The volume is not that big of a difference. So if you've been very careful and you just miss, say, the equivalence point by a drop, it really won't make a big difference in your calculation. Now, if you do a titration like, you know, maybe I did when I was younger, and I would just open the thing up and just let it flow in like there's no tomorrow, shut it and go, hey, I got pink, I'm done for today. Good day, 3 titrations, 3 minutes, I'm done. not the proper way to do titrations, by the way. But, you know, if you just kind of opened it up and you go, oh, I got that really dark pink, I probably didn't miss it by very much. You might have, because if you weren't really being careful with how much you're adding and you really just way jumped over the equivalence point, you could find yourself way over here, which means now your volume for the equivalence point, there is a big difference. So when you physically do a titration, if you're very careful, kind of proceed very slowly, even though you may physically sort of see a big color change that happens with just one drop that's added, it's probably not that critical because you're still probably very close to the equivalence point volume. But again, if you're not being careful, you just open it up and let it flow freely, and you jump to that really big pink color, then it is a problem in terms of your calculations. So in a titration problem like this, what we typically do is it's basically a solution stoichiometry problem. We use stoichiometry to really back calculate, you know, what the concentration of something is in a titration. So let's take a look at a problem here together to see how we sort of approach this. So what volume of 1.42 molar sodium hydroxide is required to titrate 25 milliliters of 4.5 molar sulfuric acid? So in this setup, for example, what we have going on in our Buret, for example, is our sodium hydroxide. And what we know about the sodium hydroxide is the molarity of it. It is 4.20 molar. We don't know the volume. That is ultimately what we're trying to find. So this, in this case, is the sodium hydroxide is our unknown. Down in a beaker, in a flask, whatever you like to use, we have all our sulfuric acid. And we know two things about this guy. We know we have 25 milliliters of it, and we know the concentration is 4.5 molar. So this is a titration problem. It obviously says titrate. Another very common one is like a problem where it says something, how much to neutralize, is another sort of titration type situation. So it is going to involve stoichiometry. So we got to start with, first off, an equation. So we're going to take all the sulfuric acid and we're going to react it with our sodium hydroxide. Now, when we do this, this is really an acid-base reaction. So if you remember, when we react an acid plus a base, as we talked about, we basically make two things. We make a salt and water. It's really a double displacement reaction. That's positive, negative. That's positive, negative. But where does the water come from? Well, the water comes from really the H from the acid and the OH from the base. So that's basically where our water comes from here. And where does the salt come from? It comes from really the other two things that are present, and that would be the sodium and the sulfate coming together. Remember that we do want to put these guys together properly. So when we take sodium, which is +1, and put it together with sulfate, which is -2, we actually get over here on this side, color coding it here, we get Na2SO4. Any questions on that? Again, it's really a double displacement reaction sort of happening here. Now, in addition, like we talked about with stoichiometry, we need to make sure that everything is balanced. So in this particular case, I think we need a 2 there, gives us 2 sodiums there, and I think at this point we might need a 2 in front of the water. Going to give us 4 hydrogens, 2 oxygens, plus 4 more, 6, and 2 sodiums. So I think that is our balanced equation at this point. Any questions on that? So how can we do this stoichiometry problem? And is it a regular stoichiometry problem, or is it a limiting reagent stoichiometry problem? So we can really analyze this by looking at the pieces of information given to us. So in terms of the sulfuric acid, we know we have 25 milliliters, as we wrote out before, and 4.5 molar. In terms of the sodium hydroxide, we're looking for the volume, and we have 1.42 molar. This problem is a basic stoichiometry problem. The reason for that is from this two pieces of information here, I could definitely get moles. From these two pieces of information, I cannot get moles. There's no way to get moles because we're looking for the volume. So because we cannot get the moles of both of our reactants, it's really just a basic stoichiometry problem. Any questions on that? So we're going to treat it like a basic stoichiometry problem, which means the first thing we did is we balanced the equation. The second thing that we want to do is convert to moles. In this case, the only thing that we can convert to moles is our sulfuric acid. So we're going to do that. This is a case where we were talking about earlier, and the question was towards the end there of lecture, what do I mean by standalone? And this is going to be a standalone calculation where we are using molarity to figure out the moles, which will be liters times molarity. That means that the volume I am dealing with right here absolutely has to be converted into liters. So we do need to convert this guy into liters. We could divide it by 1,000, move the decimal place, whichever way you do that, we'll convert it into 0.025 liters by, again, dividing by 1,000 basically here. Question on that? All right, so now that I have this, I got my 4.5. I'm going to use that like a conversion factor like we talked about before. I could use it like that. I could also flip it. In this case, I could use it just like that. So using the molarity of my sulfuric acid, 4.5 moles per liter. Liters will cancel. And at this point, we have 0.050 times 4.5 gives us 0.1125 moles of sulfuric acid. Any questions on that so far? Now, you may be wondering, what is the goal here, right? So the goal here is to figure out the volume for our sodium hydroxide. So the goal is to figure out this for our sodium hydroxide. What do we have for our sodium hydroxide? Well, we have molarity at this point, which means the one thing that we're missing in order to get to the volume is the moles of sodium hydroxide. So that is where, again, our stoichiometry comes into play. We would do step 3, which is our mole to mole relationship here. What is our two guys we're interested in? It is the sulfuric acid, which is what we started with, and it is the sodium hydroxide, which is where we want to end up. So looking at the equation, we see 1 mole of H2SO4 gives us 2 moles of sodium hydroxide, and that again is what we're going to use as a stoichiometry part, 0.1125 moles of H2SO4. To cancel our H2SO4, it will go on the bottom there, and that would get us 1 mole of H2SO4 to 2 moles of sodium hydroxide. And at this point, we basically multiply that by 2, going to give us 0.225, 0.225 moles of sodium hydroxide. Let me try to straighten out that writing there. Any questions on that so far? Now, another very common difference between a regular stoichiometry problem and a solution stoichiometry problem is actually this very last step, which is step number 4. So if you remember in our basic stoichiometry problem, at step number 4, we're going to convert moles to some other unit. Normally in regular stoichiometry problems that we've done up to this point, we've taken those moles and converted them into grams using the molar mass. Here, though, we're not going to use the molar mass because we're looking for a volume. So we're going to use the molarity. And now we're going to use the moles to solve for the volume. So our last step would be our liters equals moles divided by molarity, which means the moles we just calculated for our sodium hydroxide, using the molarity of the sodium hydroxide as a conversion factor, 1.420 moles per liter of sodium hydroxide. Here we're actually going to divide by that molarity, putting the moles on the bottom per liter of sodium hydroxide. Tells us that we will end up with 0.158 liters of sodium hydroxide is needed. You can multiply that by 1,000 to convert it into milliliters, or can move the decimal, is 158 milliliters of sodium hydroxide. So hopefully you can see that it is the same 4 steps of our basic stoichiometry problem. Really the major difference is step number 1. Again, our step number 2, we didn't go from grams to moles, but we went from volume to moles. And step number 4, where we didn't go from moles to grams, we went from moles to volume, also using molarity. So that's a very common sort of example that happens. Any questions on that there? Okay, so why don't you try one here? Okay, why don't we say we, let's do, if it took, I'll just make up some numbers. We'll go with 25 milliliters of 0.25 molar calcium hydroxide to neutralize. Why not? We'll do 35 milliliters of nitric acid. What is the molarity of the nitric acid? All right, so take a little bit of time here and see what you come up with. I'll do it as well since I just made it up, and we'll hope for the best and see what you come up with. Say something like neutralize, which is, kind of the same idea. Remember that when we talk about acid and bases, sometimes they're referred to as acid-base neutralization reactions, right? So again, that's another sort of little word that, usually indicates probably like a titration type situation is sort of happening. So again, it's really a stoichiometry problem. So we want to kind of start the same way. We need a equation. So we have an acid, which is our nitric acid here. And we have a base, which is our calcium hydroxide here. And again, we're going to get the same thing as we did before. So we're going to make water. Really, again, the water coming from the hydroxide and the H. That means that the calcium, the nitrate will come together. Remind you that the calcium is +2 in charge. The nitrate is -1. So you want to make sure when you put that together, again, you get the right formula first, and then you worry about the balancing. So in this case, the correct formula would be Ca parentheses NO3 and a 2 on the bottom. Any questions on those formulas there? Now that we have the right formulas, like we talked about, we want to make sure it's balanced. It's not, so I think we lay up a 2 there and perhaps a 2 there, and I'm out of 2's, I think, at that point. That is 4 hydrogens on both sides, couple 8 oxygens on both sides, and a calcium on both sides, so we are balanced at this point. Any questions on that? Okay, so in this case, if you're not sure, again, if it's a basic stoichiometry problem or it's a limiting reagent problem, you could just line up the information. So in this case, we have the volume given to us, which is 35 milliliters for this guy. We're looking for the molarity in this case. For calcium hydroxide, we have the volume, which is 25 milliliters, and we have the molarity. So in comparison of our information for nitric acid here, there is no possible way, obviously, for you to get to moles. So no way to moles, right? Here you have volume and molarity, which will give you to moles. So what this really tells us is we basically have only one piece of information. It is not a limiting reagent problem. We could approach this as a basic stoichiometry problem. A reminder that it is only a limiting reagent problem when you could get the moles of both of the reactants. So in this case, we can't do that. So just a basic stoichiometry approach here. Any questions on that? Clearly, that means those 4 steps. So we got step 1 done. Step 2 is we want to convert to moles. And obviously, as we just looked there, it is the calcium hydroxide is really the only thing we can convert to moles. Because again, we're doing just these 2 guys together in a calculation, not a dilution. We do again need to convert the volume to liters for it to properly cancel out. That will give us 0.025 liters divided 25 by 1,000. Using our molarity of our calcium hydroxide as a conversion factor, 0.25 moles per liter of calcium hydroxide here. Again, that is what the big M stands for here, right? 0.25 moles per liter. We do it this way so that the liters cancel. And if we do that, we end up with 0.025 times 0.25. We end up with 0.00625 moles of our calcium hydroxide. That is good, but really, in order for us to get to the molarity for our nitric acid, we're missing moles. So that is where the stoichiometry is going to come into play. We're going to use stoichiometry really to come over here to figure out how many moles we have of nitric acid. And that would be step number 3. So we would go to the equation, find the 2 things we're interested in, and we see that there are 2 moles of nitric acid for every 1 mole of calcium hydroxide we toss in there. And we would use our number we just got there, 0.00625 moles of calcium hydroxide, using this where the nitric acid ends up on top. So we get to nitric acid. The calcium hydroxide goes on the bottom, so it cancels. Moles will cancel. Going to now give us, basically multiplying this by 2, 0.0125 moles of nitric acid. Any questions up to there? So step number 4 here is convert our moles. In this case, we want to actually convert our moles into molarity. So molarity is moles per liter. So we obviously just calculated, very crooked arrow there. We just calculated the moles. In the original problem here, we were given really the volume. Again, here the volume is not in liters, so we do need to convert it to liters here, but we do have this guy as well. Converting that into liters, again, move the decimal place or divide by 1,000. Gets us 0.035 liters. Final move here would be to take the moles we just calculated, divided by the volume of nitric acid that has been converted into liters. And if we do that, looks like we end up with 0.357 moles per liter of nitric acid. Or you could write 0.357 big M nitric acid. Question on any of those steps? Again, hopefully you could see it is the same 4 steps that we talked about in a basic stoichiometry problem. Just again, a little bit of difference using molarity on the front end and molarity on the back end. Any questions on that there? Questions on titration problems, solution stoichiometry problems? Any questions on that stuff? Okay, so just to kind of finish up here, talking about solutions, we've talked about molarity, which again is really the most common sort of unit of concentration that is used, but there are different units. So for example, percent by mass, this is what is sometimes referred to as percent M/M, and M/M means mass to mass, so percent mass to mass. It is the mass of the solute divided by the mass of the solution times 100%. Very important in these type of problems, though, is they will give you the mass of the solute separate from the mass of the solvent. So it's really important in the bottom part here that you actually get the mass of the solution. It's a very common mistake that people will divide by just the solvent. And again, in these problems, they typically are given to you really separate from each other. So what does it mean if we did have like a 4.5% by mass, say sodium chloride solution? You could actually turn this into sort of a usable conversion factor by basically, when we have a percentage, we assume 100, right? So if we had 4.5% by mass, that means there is 4.5 grams of sodium chloride and 100 grams of solution. Or you could use it as a conversion factor the opposite way. 100 grams of solution has 4.5 grams of sodium chloride. So sometimes you could plug and chug into this equation as well, but you could also kind of use the percentage as sort of a conversion factor to help you out as well. This is actually not the only percent concentration that is used. There's also percent volume to volume, like in alcohol. And that is the volume of solute divided by the volume of solution times 100%. There's also percent mass to volume, which is the mass of the solute divided by the volume of solution times 100%. Top guy is basically milliliters divided by milliliters. Bottom guy is kind of grams divided by milliliters, like density. And these are 3 very common units of concentration, kind of percent units. And it works the same way if you had a 4.5% by volume sodium chloride solution, it would mean that you would have 4.5 milliliters of sodium chloride and 100 milliliters of solution. Or in 100 milliliters of solution, you have 4.5 milliliters of sodium chloride. And same thing for this guy. You had a 4.5% mass to volume. that would mean you had 4.5 grams of sodium chloride. This was sodium chloride per 100 milliliters of solution. Or again, you could use it as a conversion factor like this, 100 milliliters of solution, 4.5 grams of sodium chloride. So again, sometimes it's helpful or useful to kind of convert these guys into like conversion factors, do a dimensional analysis problem. You could also just plug and chug into the formula as well and solve for it. It does come out really the same. Any questions on that there? So let's take a look at one then. A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. Calculate the mass percent of calcium chloride. So what we're looking to calculate with here, since a lot of it just pops up on the screen, we'll talk about it, is the percent mass to mass. And again, that is our mass of our solute divided by the mass of the solution times 100%. When we have 2.5 grams of calcium chloride, that is the smaller part, and that would be our solute in this case. 50 grams of water, that is actually our larger part, and that is the solvent. So when we would go to do this, it's really important. Obviously, this would be our solute, which would be the top part. But we don't want to divide by 50 because, again, that's only the solvent. So we need to add both of these together to get the actual mass of the solution. And if we do that, we would take 2.5, which is our solute mass, divided by 52.5, which is our solution mass. Again, that contains both the solute and the solvent together. Times it by 100 gives us a 4.76% mass solution of calcium chloride. And again, you would use percentage here. You would also maybe sometimes write it like this, percent m/m calcium chloride to indicate that we're talking about here mass to mass. Question on that calculation there. So again, the kind of critical part where people kind of mess up is that part with the solution. They sort of forget to add in the solute to the solvent. All right. So why don't you give this one a go here? Concentrated hydrochloric acid contains 37.2% by mass. What is the mass in grams of hydrochloric acid? That's in 35.5 grams of the solution, basically. To see what you come up with, take a moment. Percent. So we can look at our equation here. Mass to mass is the mass of the solute divided by the mass of the solution times 100%. And you could plug and chug in. You got the percent mass to mass. You got the mass of the solution. You can obviously just plug and chug into there and solve for it. I'm personally going to do it more of a dimensional analysis conversion approach just to kind of show you how that would work. What the 37.2% by mass would mean is we basically would have 37.2 grams of hydrochloric acid in 100 grams of solution. Or again, we can use it as 100 grams of solution would have 37.2 grams of hydrochloric acid. We know the grams of solution we have, so it would be 35.5 grams of solution. Using more of the dimensional analysis approach, we would use this as our conversion factor. And that would give us 37.2 grams of HCl and 100 grams of solution. Grams of solution will cancel, gives us 35.5 times 37.2 divided by 100 gets us 13.2 grams of hydrochloric acid is dissolved in that solution, basically. By the way, this is the exact same math you would get if you rearrange this correctly. You would basically take 37.2 times 35.5 and divide it by 100. Again, works out the same way. Question on percent concentrations here. Now, another important concentration that we do see a little bit along the way, hopefully they agree with us, is what is known as molality. And we do see this a little later on in the semester, but let's just be very clear here about a couple of things. Molality is not molarity, and the abbreviation is a lower M. And it actually is, the molality is moles per kilogram of solvent. So it's actually moles per kilogram of solvent, not to be confused with big M. I'll do it for dramatic purposes there. Big M is molarity, which is moles per liter, right? Molarity. Versus little m, which is moles of solute per kilogram of solvent, and that is molality. So they sound very much alike. They use kind of the same letter, but one is capital, obviously, and one is lowercase, and they are a little bit different. It is kilograms of solvent on the bottom. Again, no molarity and stuff like that. So it works very similar. If you had 4.5 molal sodium chloride, that means that you have 4.5 moles of sodium chloride in a kilogram of solvent. So it kind of works the same way. How do we kind of go from really molarity to molality? It's usually density is really the guy that sort of ties those two together, grams per milliliter. Also, sometimes you may need to use density to figure out the mass of a solvent. Again, you may be giving the volume and the density. So remember, density is mass divided by volume, which means mass would be volume times density. So you sometimes have to use that with the solvent in these type of problems. And again, sometimes you have to go from grams to kilograms again to make sure that you sort of calculate molality correctly. So let's take a look at an example of that. We want to calculate the molality of a solution that's prepared by dissolving 61.7 grams of C3H7OH in 175 milliliters of water. So again, here we're looking for molality, which is our moles of solute over kilograms of solvent. Water is our solvent. This guy right here is our solute. So we have the grams of our solute, so we do need to convert it to moles, right, to get the top part that we need. So we would take 61.7 grams of C3H7OH. We would go to the periodic table and calculate the molar mass. That is 3 carbons at 12.01 plus 8 hydrogens actually at 1.008 and 1 oxygen at 16. Looks like we get a 6009 as our molar mass here. 6009 grams per mole of our C3H7OH. Grams will cancel, and that would get us 61.7 divided by 60.09 gets you 1.03, we'll call it, moles of our C3H7OH. That is the top part that we need. Our water is our solvent, and we need the kilograms, but here we have the volume and the density. So as we were just talking about, we could use the density equation to solve for mass. Volume times density. That means that we have 175 milliliters of water. density of water is 1 gram per milliliter. I think I could do this math. Gives me 175 grams of water, which is our solvent. That is not what we need, though, because the bottom here for molality is kilograms. So we do have to do that conversion. We got to take our 175 grams of water, and there is 1,000 grams in a kilogram. So we're going to divide that by 1,000 or move the decimal point over, going to get us 0.175 kilograms. We now have the bottom part that we need. Putting both of those together gets us 1.03 moles per 0.175 kilograms. Going to get us 5.89 moles per kilogram. Or again, you can, much like molarity, write 5.89 little m in this particular case. Question on molality here. We won't see a lot of it until kind of almost the last chapter, second to last chapter, when we talk about colligative properties. We see a lot of it at that point. Any questions?
Just a quick, the units under the m equals mole or the solute, is that kilograms? Circled?
Right here on top?
Yeah, on top.
That is kilograms of solvent.
Kilograms of, okay, thank you.
You're welcome. Other questions? Okay. So again, I won't say you use molality a lot. You do use it with colligative properties, which we'll talk about in a later sort of chapter, but we will see it again. So again, molarity in terms of solutions in general, capital M, is really the more common one. But again, this sort of unit does sort of come about occasionally here. Any questions on that there? All right, the last sort of unit or concentration type thing is what is sometimes referred to as mole fraction. And we'll actually see mole fraction also with colligative properties. And we'll actually see it in the next chapter, which is about gases. But a mole fraction is kind of what it sounds like. It's basically a percentage without multiplying by 100. So it's kind of like 1 is your biggest number you could get. So it's basically the number of moles of what you're interested in divided by the moles, the total moles. So for example, if we wanted to calculate the mole fraction, which is abbreviated with a big X, of say A, and we would take the moles of A divided by the total moles. We just wouldn't multiply it by 100 here. So if we had a solution that had moles of A plus moles of B floating around, that would give us our total moles. And if we wanted to figure out the mole fraction of B in that sort of solution, we would take the moles of B and divide it by the total moles. So mole fraction is really like kind of like a percentage without the percentage part. And that means that because we're not really multiplying by 100, if we wanted the mole fractions for each of those, they should add up to 1 when it's all said and done, because 1 would represent 100% since we're not multiplying by, again, 100 in this particular case. So looking at an example of this, which calculates the mole fraction of methyl alcohol in a solution that has 0.328 moles of methanol and 0.929 moles of ethyl alcohol. So the first thing we would want to do is figure out the total moles. So since this solution basically has 2 things in it, ethanol and methanol, we basically would just add up the moles of each of those. So 0.328 moles plus 0.929 moles gives us a grand total here in this solution of basically 1.257 moles floating around. So in this case, we're interested in the mole fraction of methanol. So The mole fraction of methanol would be the moles of methanol, which is 0.328, divided by the total moles here, which would be 1.257. And that gives us 0.328 divided by 1.257. We'll call it 0.261 would be the mole fraction of methanol in this mixture. It's essentially 26%. Yes, is basically what it is. Again, we don't multiply it by 100. We could also do it for the ethanol part. The mole fraction of ethanol in this case would be the moles of ethanol, 0.929, divided by our total moles. Again, not multiplying by 100 here. It's a 0.739. Basically is 74%, if you will, of ethanol in this case. You also could have, like I mentioned before, you could have took 1 minus 0.261. We'll give you this number as well. So that's an alternative approach. That's like taking 100% minus is what you got there. So mole fraction, not too hard. Again, comes up in, we'll see it in gases in the next chapter. We'll also see it later on as well in colligative properties with molality as well. Any questions on that there? If I'm not mistaken, that should wrap it.